The purpose that I will of how each input feature influences neuron. Sorry. Recent work, I mean recent work, but it's like 5 years old. I maybe I don't know when this paper is from though. Has explored the application of information bottleneck principles to representation learning in neural networks. Proving new principles for the conductance of explainable AI. Yeah, I mean my impression of most explainable AI stuff is that they kind of not very useful because they are all looking at things like how the input affects the output, like just doing grades on the input and things like that. That even the explainable, I even heard like people working on this kind of thing saying it's not very useful. But yeah, this is process of neural conductance to quantify the importance of individual neurons, which extend to a layer level of analysis. But if you want the importance of a neuron, why don't you just do for some input, just do the gradient for that from the neuron to the input, and you have a nice linear approximation. Maybe this has other nice properties, but no. Conductance promise a determine how input features influences how the neurons in a given layer, allowing researchers to gain insights into the internal worlds and network. Layer conductance is related to network dynamics because it captures the gradient-based contribution of the input features of the division layer. Wait, are they used? Using the derivative of the division function contains are they just is that just a fancy name for taking the gradient of the derivative of the division function contains. I'm being confused. Is this just the same as taking the gradient of the input on some output, like on some layer on some output with a fancy name? I guess so. I don't know. Did they get
Does the gradient have the X term? Isn't the gradient just the first one, like the first bit, the derivative?
Yeah. I guess you multiply by the input. Maybe that's. But wait, isn't this like the gradient of the? I'm not sure what this, but it's over t over x, so it's like the gradient of the input, right? Anyway,
Yeah, they explain later that T represents the activations at a layer L.
yeah. So this is just the typical thing people do in Mech Interp of taking gradients of activations for some output and checking how much that matters for things like activation patching and things like that. Right?
They weight it by the input? Is that I don't know. I'm asking like
I'm not sure either, but maybe it'll be clear if we keep running and look at the other things. But those might be surprised, but maybe all of this is just doing the same kind of thing people are doing, more like typical Mech Interp papers, but using different names because it's come from the explainable AI literature thing, and they have different jargon or whatever, but not completely sure. What the difference between so the The deep networks can be studied with the lens of information theory, particularly information modeling. Several the surface event in this framework. The information paths in neural networks could not be monotonic. What does it mean for the information paths in a neural network to be monotonic?
I think it
So
kind of
this is-
explains the next line.
Delicate mutual information between T and Y or X should decrease monotonic across layers. The concept of a unique information path of information plane relation in idealizing conditions. Real world data that never can lead to the basis of ideal path according to data processing inequality. Yeah, whatever, but yeah, it makes sense that in practice neural networks don't have a single path, they have multiple. I'm not sure why this information bottleneck theory will predict that there is a single path or something. But I guess maybe if you are thinking that the model is compressing things and it will be better for that if it was a single path, but no, according to the processing inequality. Okay. Critical foundations. The concept of neural information plane plots mutual information in 2 dimensions. Okay, I guess this is just mutual information. On the x-axis, representing the mutual information between the hidden layer, and this is just the activation of the hidden layer, I guess, and the input x, and the output. Processor information transformation progression. Okay. Yeah, this seems to me like the kind of thing I was thinking, which is just they have some simple number that doesn't actually explain much about how the model actually works, where you get some mutual information between the output and the activations. And maybe I guess it's true that it may, this kind of broad measure maybe does tell you something about how, like, our training dynamics, where there is some change in the model, where at different phases it's learning different ways, and the whole measure changes. I do expect like this the kind of thing that works better on a smaller model on its task, or things like ImageNet or whatever, where the model just learns that, than in something like a large language model, when it is more complicated because it's learning a lot of things. Maybe it's useful now. I don't know what the virtual information has to do with these conductance things they were talking about earlier, but okay. It's possible to identify, model information. Model information is defined as this formula, which is where x and y are 2 random variables. This is the joint probability, x and y. S and py dimensional distributions, and it's just a big sum of that. Information plane pursues mutual information quantities. Mutual information between the input and the hidden representation, and mutual information between the expression and the output. Okay. How much information each layer retains about the input, and how much information it has about the output. Okay. Then, information plane dynamics. Neural relations involving the information plane. The dimension server. Compression phase. Early in training, layers retain a lot of information about the input. Over time, layers can develop information, like introduction in the output. In the input one. Now was the compression phase. Okay, so it's not the thing I was thinking. So it's not like related to the thing on the Grokking paper. Maybe it is in some indirect way, but it's about how much information about the inputs the the different layers have. I do wonder. I mean, early in training, I will guess the part of the reason thing the layers have a lot of information at the start because there is maybe not in whatever image models they are, but usually there is things like skip connections, and makes sense that later model learn to actually store things there that are not the thing that the skip connections are. And the synchronous kind of put having a lot of information as the default, I guess.
The reason is like for the reason for why the early training retains a lot of information. What do you think causes the loss in information from the input? Because if it's a neural network, there shouldn't be any like non-linear transformations, or maybe just the amount.
I mean, there are because there is different. You have ReLUs and all that, but also you only with linear transformations you can remove, like, if you think about in the terms of, for example, a transformer with the terms of the paper of the circuits paper where they talk about the residual stream, you can think of the layers of writing things to the residual stream that might like override things that were there earlier. So you will expect that as the model learns more abstract things, the model will, you will start finding increasingly less, like on the later layers, you will start increasingly less specifically, like increasingly less the things directly on the input, like tokens, and where you for example on the large language models, and you will find more abstract concepts instead. Although I guess you will still expect this abstract concepts to be in some sense having for mutual information with the input, so it's not exactly that. I guess you will still lose some things because you only, like, kind of, they also say this, but you only care about some specific parts of the input, so you might just delete some things that you don't care about, or only, replace things by some more abstract versions that only care about specific things about the input. Also, at some point on later layers, you want to start, in some sense, composing the outputs. So you will start seeing, I guess, like the things stop having mutual information with the input, start having mutual information in the output, in the sense that the later layers are in some sense, like, the model already knows what the answer is and is trying to write the output so an embedding output is the right thing. Yeah, I wonder if you run this kind of metric on different models. I have some ideas, like in the Lila chess model, for example, where it does the search thing. Maybe you'll find that after specific layers where the model seems to already have moved the information to the correct square where it's going to output the correct move. Maybe it's has higher, like, stop the X, the mutual information with the input goes up and goes down. But yeah, I don't know how useful this metric is, I guess. Okay, fitting phase. Mutual information between the hidden representation and the output increases, indicating that the network is learning useful features for the task. Layers, I aim to maximize this
while minimizing this, achieving a balance between retaining relevant information and discarding noise. I'm not sure why, like, this makes sense. I'm not sure why they want to they say they were trying to minimize this. I guess if you think of it in terms of compression, the model wants to have a smaller representations that only have the things that are important for the output. Yeah, but I guess it's probably coming from this information bottleneck. Deciding to find the comparison representation T of the input that retains as much information as possible of the output Y. And the objective is to optimize the following trade-off. Okay, so they're saying that the model basically compresses the input in some more abstract representation, which is kind of what I was thinking. Which I guess this information bottleneck theory. I'm not sure that's exactly always true, but they already mentioned that there is more than one path and things like that. I guess in general, I think this kind of measure is neat to do some simple analysis and things like that, but it's not. Maybe there is some broader thing about training dynamics that you can understand or look at the thing, but I don't think it is going to help us that much to actually understand. The things they say on the Astra where they actually understand models, because it's like too broad. Like you're just looking at the mutual information of the entire layer, and you're not going to figure out like what the specific circuits actually do. But yeah, concept of layer conductance. Anyway, yeah, going back to this. So compression accuracy. Okay. Layer now let's see what this layer conductance is about, because they haven't actually used it yet. Different span right, and it's used to interpret contributions from input features to activation within specific layers of the neural network. Okay. Conductance provides a view of how each input influences the neurons of a given layer, allowing researchers to gain insights into the internal workings of the network. Layer conductance measures the sensitivity of the activations in a neural network layer with the respect to the input features. And I guess this is interesting in that if I need to be sure later that that if it seems the same thing as other kinds of things related to graded people doing Mech Interp, maybe if I do something related to that at some point, they can cite the explainable AI things under conductance. Oh, someone is writing on the chat. Oh yeah. Yeah, I'm also confused by that. Like the someone is asking why conductance is multiplying by the input. Like, and that makes sense. Like I don't know sure why they have the gradient with respect to input and they multiply by the input. I guess you will get if your input is the image. Yeah, I guess it's this kind of thing with explainable. I think where you have your input is typically an image, and you want to get some kind of heat map of which parts of the input matters, or something. But still, going to be weird, right? Because you will want that to be on the shape of the input, but what do you care about? Like it's not isn't that going to basically be like you have how much the input matters for different parts, and you like if you're manually doing it within an image, you will get like the image, but like it's brighter on the parts that matter more or something. It does seem a weird thing to do now that you mention it. If I understand it correctly, at least. Which I'm not sure at all I understand it correctly, but. Maybe we will need to actually. Also, I'm waiting because people are writing on the chat. But yeah, maybe we will just need to actually read some of these conductance papers or whatever and see why they do that exactly. Having a set of activations, how much of the value of y was contributed by a particular ty? No, but here they are doing like they are not talking about the input right now, right? Or how do you get? Is the idea that since if you take the gradient and multiply by the input is like doing some approximation of running it through the network or something? But like they're taking the gain with respect to the layers, right? Not with respect to the output. Or I guess maybe the last layer is in some sense equivalent to the output minus the embedding. But yeah, not sure. Like this seems to be about okay. Like this seems to be about how much the input influences the some activation of some layer, right? Maybe okay. Here we could have just keep reading of it. Interpretation of layer conducers. Hopefully they'll be actually explain it. The layer conducer function can be expanded as follows. Right, so some of this is basically the same, but for all of the layers, I guess. No, for the inputs. It's for a specific layer. Yeah, so it's the conductors for some specific layer, and it's doing it for a bunch of inputs. Yeah, input features. Oh, but it's input features. What does input features mean in this context? I guess they have some classification of input features or something. I don't know. Like if you're here the input is images, so I don't know what they mean by input features. Sadly. The conductancy not only measures the sensitivity of the activations to the input changes, but also incorporates the actual values of the input features. The integration of X into the conductance calculation highlights the dynamic nature of information flow and gives good view of how information is transformed and preserved within the network. Okay, so I guess they can take the input and divided somehow in some set of input features, whatever that means. And with this, they can get how much each feature matters for the output, I guess. You couldn't do that taking the gradient over the input features anyway, too. Yeah, no, I don't understand it anyway. Have you say it? Yeah. Maybe they have some example at some point. Information plane with layer conduct. This is I don't think this really explain much, but okay. Information plane with layer conductors. The conductor-based information plane uses coordinates. I see. So is the mutual information where the conductance is with conductance? Yeah. Why do you want to do this though? Conventional relevance. How much the information captured by the layers conductors is directly relevant to the final prediction? High indicators the layer influence is highly informative for the task. Yeah, I'm not sure I understand why you want to do this instead of want to do the directly with the input and output and activation from each layer, whatever. Contributions to the actual predictive power of the model. Feature important spread has high considers that the features it captures are important for the task.
Could be that your actual activations might not be as informative as how they're changing over your inputs. So that, if you're hitting low gradients, those are probably not important. While those with like
Yeah.
higher gradients are like more where like the flow of information is. And so eventually what you'd want is something that's predictive of the output rather than a reflection of the input.
Yeah, I still don't understand why they need to multiply by the by the input here instead of
Yeah, I'm looking at
doing-
it too. So yeah, I feel like it has to come from something. It has to come from like some. I'm thinking maybe like flux or flow. I don't know. I'm looking
like it
things up,
feels
but I
like
can't
you
quite.
could do everything with the gradient instead. You know what I mean? It seems like I don't understand what adding the input, how adding the input change things because this you could do the mutual information between the gradient and the output, and that makes sense as a thing. I'm not sure what doing this conductance thing instead helps with. But yeah. Also, wait a minute. Maybe the assumption is that the gradient is mostly constant, so the gradient multiplied by x is like a first grade degree Taylor series. Yeah, I don't understand enough math to know what you're talking about, but I maybe. So someone left. Anyway. Mathematical foundations of the conductor-based information plan. Maybe they explain something. Where J is the Jacobian matrix of the activations with respect to the inputs. C is a deterministic function of X. The mutual information can be expressed as this thing. Okay, so Jacobian matrix of the activation. Yeah, I don't think I'm going to be able to understand all of this right now. On the input dimension, correlations and dependencies among the input dimensions. Set the output y, which is a constant for a given problem. It represents the centrality in the output layers for an information considered. Yeah, I don't know. I mean, yeah, this is just obviously high mutual information between C and Y means that C has information about Y. We don't need a lot of math to know that.
But maybe that's why they use they multiply the gradient by X though, so that this like entropy of CL is basically like the entropy of CL given X goes to is like 0. Is that what that like implies? That's quite confusing for me though.
Yeah, I have no idea, to be honest. I'm tempted to just. I mean, Sion did warn me that this paper was was also complicated, but I didn't have a lot of other ideas and wanted to leave the other one for like trying to get the authors. So I guess I can keep going a bit. And hopefully next time it will be easier, but yeah, not like the understanding of it. Information transformation efficiency. Expressions to analyze the networks. Like I feel like I could probably understand if I spent some time like looking up terms and trying to remember math and stuff, but I don't feel this is interesting enough to motivate me to actually do that. There is another paper that I might do for a future reading group that does actually it's more Mech Interp that does actually seem also hard, but maybe I'll try to read it beforehand, try to understand it more. It's about transformer learning causal structure, but Sion suggested this one first, so I'll do that one later. Anyway, information transformation efficiency. Let's I guess I'll do a quick. Let's see what. So you have information compression efficiency, whatever. It's the different layers. Relevant information. Guessing user information. Yeah, whatever. Nice plots. What else is this? Attribution by complaint analysis. Oh, so mutual information. So they do X mutual information by layer. So like layer, and this is the mutual information with the input. And maybe looking at the figures is better than trying to understand the math. So yeah, this is basically what makes sense that the mutual information with the input decreases, like as they were saying, and increases, and the mutual information by layer, the output increases, and then decreases for some reason. Wait, this is standard deviation, though. By no. Okay. This is a good one. Okay, but this was the information about the theory. This layer processes input sorry for the previous layer for the microconcept. Yeah, that's not true. But I like in some sense, yeah, but I mean you don't have skip connections, but in some sense, yeah, but in practice you mean like you have the input from the previous layer also comes to the layer before. That was they mean. These inequalities imply that the information about X or Y that is lost in one layer cannot be recovered in subsequent layers. However, empirical observations using the ResNet pre-trained network on the image datasets as well as other networks on different datasets reveal that the mutual information can sometimes increase in higher layers. Those instances where okay. Okay, so mutual information can increase in height between the information between what and what. This is XA and XA where L is okay. So like the one for the input is higher on a higher layer, sorry. Yeah, where the thing is goes backwards. Like this one or whatever this is. Did someone write? Oh, yeah. But sorry, but no, then someone wrote a word on the chat. Is the function in a small linear neighborhood we can approximate it to be linear? Let's just say for the sake of the sample that this approximate. I'm reading the thing that super stealthy ship, whatever your name is pronounced. Yeah, is said. Sorry, in a small enough neighborhood we can approximate it to be linear. This kind of breaks. Okay. Example that this approximation is for example, let's say that we're looking at the point. If I know that this functions and the ones into the output of the points. I'm not sure I understand the example either, sorry. Especially because I'm getting annoyed by the text thing, but I don't know if I will get I think it's kind of getting late, so maybe I'll just read the conclusion and leave it here unless people want me to look at some specific part or something. And next week, hopefully, we'll get an easier paper that is like more about Mech Interp. Specifically.
Is this
Yeah.
if what I understood what this was just showing a different metric to look at the models. It wasn't really anything to.
Yeah, I mean, maybe it's interesting. Yeah, this is basically just, as I understood it too, is basically they do this, they have this fancy metric that you can use to look at the model, and they also do something related to, there is some earlier hypothesis about how one of these, hypothesis about how model dynamics that people have that let them tend to just be wrong, and they show that this seems to be empirically wrong. Something related to how you will expect the mutual information to go down and then go up. And Cantos does that, but does not. It sometimes, like the mutual information with the input to go down, and then the mutual information with the output to go up. But sometimes that doesn't happen. It goes the other way around instead.
No, it does go down, but then it goes back up, which is I think interesting because it goes back up with y with the mutual information of y. So it feels like it in the end it needs both, it needs to form the mutual information basically between x and y.
Yeah. I guess that's like I guess I wonder if not sure if the image things have like the image models they are using have skip connections, because I feel like that matters for
Yeah, I feel like ResNet should have skip connections, but let me look.
yeah,
The res and
Because-
resnet sound individual, right?
because then the model the model, since the model in the last layer can read things from later layers, the model could just be that's for skip connections. Okay. So the model can just read from a previous layer. So like maybe it's just doing things on different layers. Like for the maybe it just goes up because it's doing something on this layer that is actually just going from the if I'm sure if this graphics that is going up, but it maybe just goes up and down because it's in some sense skipping layers, like the layers where the mutual information with the output is high are just layers where the model is storing some things that then are basically skipped to the last layer maybe for the output, and then maybe on the next layer is doing something with the input. Like I guess this just shows that maybe if the hypothesis thing claims this, that the model that the neural net processes things directly from the previous layer, but I don't know. That will disprove it. I don't know what you would expect that when you have skip connections. But
but I guess we will have to actually read the other, the whatever information bottleneck thing paper to figure that out. Why they say that? But that's not true. I will also have guessed it's not true beforehand, but yeah. Maybe there is some interesting things you can do if you actually understand more about what exactly this means to actually learn something interesting about how the model works. But I'm not super excited by this kind of thing, to be honest, because it's. I mean, maybe if you can like do something more like get the mutual information of some I don't know, transcoder feature or something with some other thing. Maybe there is something vaguely like that, but some of this seems like has some of the problems that I have with a lot of the explainable AI stuff, which is that you are looking at either the effect of the input or the effect of the entire layers, and that's not that interesting because the models are actually very complicated and have a lot of different parts inside a layer, and we kind of would want to actually understand the model well to understand those. But maybe you can use the same kind of method to understand those by doing, instead of 4 layers, doing 4 parts of the input. But I guess that goes back to we don't actually know how to decompose a model into features in a nice way. And that's kind of whole Anthropic trying to make sports encoders or whatever it's about. But yeah, I think unless
I'm
people have
confused
more
though
things.
because it's not the ResNet but the VGG or whatever it is. That has like every other layer doing the usefulness. So I don't get your point with the skip connections. Like if you look at figures 1 and 2.
Yeah. Oh yeah, I don't have that much idea what I'm talking about here. Maybe I just wrong.
So
yeah.
it's the one that does like the spikes every other layer. That's the VGG 16, and that one should not have skip connections.
Oh yeah, that's interesting. I think if it doesn't have anything like skip connection, how does like
But it does
okay.
it does do like I think a compression. So I think the the things start. Does it get bigger and bigger or smaller and smaller?
Wait, this is
Oh no.
compression though. What does compression
But it's the
mean in this
same. Yeah.
context?
Oh, I forgot. But usefulness is like the information difference, I think, between it's like a ratio between like the current layer and like minus the previous layer over the entropy of like the output minus the last layer. So it's like how much more information you get out. Like I guess how much more information there is like added in this layer, right? Compared to like just the output as opposed to like the previous layer. I think it's easier if you just look at the thing because it's just like a ratio of differences.
Wait,
Yeah, that was the
see.
usefulness. That's the that's the compression.
Compression
is
is entropy of activation of layers and entropy of activation variation between layers.
So I guess if it.
Variable between layers. If you think compression is a yeah, what's else? But what is the preservation of information, which is
Limited information on the activations of the two layers. Represented relative to available information normalizes to the preservation of relevant information. Increasing useful information. People are writing in the chat. And maybe I should calculate this, but I
feel like it must be telling us something though. Like there should be, if this is useful in any capacity, I feel like, like for example, like in the VGG, like there are 3 plots that are basically like very similar in their trends, but the
this one seems to
efficacy.
just be increasing.
Yeah, no, I mean the remaining 3 plots is what I was.
Yeah.
Well, yeah, and then if you go to the ResNet, right, it's a bit different. It doesn't quite have like similar things happening across the layers, and
Yeah,
I'm wondering if
it doesn't go up and down. I mean, maybe that this has something to do with one having. So maybe
connections.
have some connections, or maybe you. I guess it will be interesting to see like other ResNet, the same architecture training on different datasets. Maybe it's just kind of random, and this is not a very useful metric because different, or like it says something about what the model is doing, but it's not like doesn't depend that much on the architecture. I have no idea.
It's just weird because it's like, the efficiency and the compression are like pretty correlated, I would say, if not like exactly correlated in the VGG, but like almost anti-correlated for the ResNet.
Wait, actually, because let me. Okay, I was just checking that it was not. Yeah, but no, yeah. Wait, this one on 5 and this on 5. Yeah, it was just maybe. Let me check it. Maybe it just was shifted one layer or something, but no, it's the same.
So that would be interesting, right? Like if because then it would be like one layer's doing one thing and the next one's doing the next thing.
But yeah, no, it seems like it's the same. What's compression and what's efficiency again? Oh, John is saying that total information is zero only for independent variables. Okay. And that, yeah, the total information between X and Y and is lower than the what's
What's efficiency? Global efficiency, maybe?
No, I was asking on the chat. Like,
Okay.
what's the y of x? Because I understand that y of x and y is the relative information between x and y in this notation, but like with only one variable, I'm not sure what it means. Ah, okay. Yeah. Okay. Yeah, it's the entropy of the. So the mutual information between x and y is smaller or equal to the entropy of x, and yeah, the mutual information is on the entropy of y. And mutual information between x and y is the same as the y and x. Yeah, but that makes sense because that's the. Information compression.
The global efficiency, I don't know how they're picking alpha, beta, and gamma. So maybe that might explain why things are different between the two plots.
And -1. Then the preparation between the ASL and -1. Increasing user information. So global efficiency was combination of entropy equation or information flow can be both entity to characterize information levels. Entropy equation captures changes in the distribution of dimensions while information flow measures how information propagates and transforming one layer. So global efficiency is a sum of C and P and U. So like the compression, the reservation of information, and the increase of information with some weights. So so the reason the information compression here is the same and the efficiency. So the global efficiency thing is a sum of the other things. So we should, so if you want to understand why this is different, you should be looking at the other ones. So here the useful information if kind of so I guess this one has it's probably the amounts because information compression here is 0.4 and on the peak, and here is smaller. So I guess and here is So basically, I think the reason why the global efficiency is almost the same here than this is because the global efficiency is just adding up all of the other plots with some
Oh, wait,
coefficient.
what's preservation? Is that the OPL? Okay. All right.
So this one it's much basically this one is lower and this one is higher, and they are this one when this one increases here and this one decreases here. So when this one looks like this on here and it's 0.8, and this one has a peak of 0.16, so it's just bigger and gets basically overwritten by this. So it's just a weird thing to plot, I guess. Anyway, does anyone want to look at some specific or talk about some specific part of the paper? Or do I just like look a bit at the conclusion and leave it here because it's been for a while and I'm not sure how much we are going to figure out? I mean, maybe someone else, if you are understanding it more, you can try explaining it or something. But yeah, otherwise I'm just probably going to just read the conclusion and leave it here.
Yeah, I don't think I have anything.
Right, I'll read the conclusion. But, someone is writing, but yeah, I'll read the conclusion while you write, and if you want to check something, we can do that after. This study has highlighted the critical importance of analyzing the flow of information through the hidden layers of neural networks using the framework of the information plane, a conductance-based approach. Our empirical results derive from pre-trained models such as ResNet 50 and BES, well, that one. On the image itself, demonstrate that certain hidden layers play a pivotal role in capturing and preserving essential features, thereby enhancing not only model performance but also interpretability. I mean, I don't think that doesn't actually help. I'm not sure why it will help performance. No, but maybe it helps something with interpretability, but we found intermediate layers effectively balance information orientation and compression, filtering out irrelevant information while retaining pertinent features for the task at hand. Furthermore, our approach revealed that deeper layers focus on compressing data and optimizing relevant information, underscoring the complexity of information dynamics in the neural networks. Yeah, neural networks are complicated. That's not a very surprise. The implications for this research are significant. On one hand, it provides more precise and analytical for diagnosing issues of overfitting. I'm not sure how you will do that, but okay. On the other hand, it paves the way for the design of more robust and efficient models capable of better generalization of unseen data. Yeah, I'm not sure how you are supposed to do that from these metrics, but maybe it's because I don't understand it. But by integrating measures of information transformation and consider the integration flow, we can gain a deeper understanding and explanation of neural network functioning, which is essential to the adoption in critical implications. Yeah, but I don't think you are going to actually. Maybe, but I don't. This feels like the kind of thing that you say to say that your paper is useful, and I'm not sure that this whole metrics thing actually got to anything super interesting. But yeah, where studies have revealed complexities and deviations for established theoretical principles, In this context, the need for ongoing research to reconcile empirical observations with theoretical foundation of deep learning. The future of modern interpretability in networks will depend on ability to navigate two dimensions, leveraging the provided approaches and such the one we propose. Okay. Yeah, my impressions of theory paper, deep learning theory papers in general, and this seems like the vibe I get from what the opinion of a lot of people is just they are not very useful, or more of them are not actually super like actually useful for real neural networks. But yeah. Let me just go through it a bit. Anyway, anyone else wants to say or do something, or do I just end it here? I'll wait like a few minutes, or like 1 minute or two.
For the paper, we
actually,
just
more like
had
a
what?
minute.
Do you have any clue what the next week's paper will be?
Oh yeah, so for the next week's paper, I sent a mail to the one of the authors of the remember the name for a moment. The robustly improving LLM fairness in realistic settings with via interpretability paper. I posted it. I put this again, I guess. Yeah, I posted it earlier, and I haven't received a response yet. But maybe they'll come. But I think we'll do that paper regardless of whether we have the outdoor. And that one seems less math and more like. This seems a lot simpler. Like it's only a few pages, and it's more about using Interp from some practical thing, so it'll be a lot easier to understand. Yeah, basically this one. I mean, basically. And after that, I'm not sure, but I do have this other paper that also seems like has a lot of math. I'm more interested in it. I might try harder like beforehand to read and understand it, which is like they make some nice data set to how in a toy task models learn, so transformer learns to do causal inference according to them, and they reverse engineer how that works. Yeah, they have a bunch of things about some Markov chain causal structure thing and how the model basically learns that. I think it's
Can you show the title?
This one, but that will be like in 2 weeks. I mean, next week we'll do. Next week we'll do. Sorry, let me go back to the previous one. No, next week we'll do this one. Yeah, after that, unless someone else suggests something better, or something important like some anthropic thing comes up, we'll maybe do this one because I thought it was interesting. Yeah, mostly because I see people on the internet arguing about whether whether models can learn causal relationships or whatever and have been bad arguments about that. And it's nice if there is if this actually works as a simple counterexample. But yeah. Anyway, I guess I'll end it here. Nobody's saying anything, or I think writing on the chat. Let me check the chat a moment. Oh, someone is writing on the chat. I wait for you to write. Okay. Yeah, I think it's the first time you come here, right? Or did you come early, some other? Yeah. Other times we get the authors of the papers and they just explain it, or like we pick a simpler paper. And yeah, there's other times that I pick some paper like this and I spend the whole hour trying to understand it. But yeah. Yeah, feel free to come to future living groups.
I have an idea for next time. Victor,
Oh, yeah.
could you
No,
like
as I said,
I-
like next week we are doing this one because I already mailed the authors. But after that we could do another one.
Yeah, Victor, instead of reading the paper continuously, why don't you like make intentional pauses regularly so people could like give comments instead of interrupting? Because I think that's might be one of the reasons why people participate less. Or maybe that's
Okay,
just
yeah, that's cool work, I guess. I mean, I feel like mostly people won't participate anyway, unless I start doing like Wuhan actually poke people to participate.
I guess like we have the people who participate either way, but I want to see if more people participate if we add
Yeah,
intentional.
I guess I can try that next time I have to.
Let's maybe measure how many
to
people
do it to run it myself.
Maybe it might work.
Yeah, I'll try. I honestly not thinking about that. I'm mostly just reading the paper and hoping someone else says something so I don't have to spend the entire hour talking alone. But
next week's paper, do you want? I guess that sounds cool. I'm pretty excited. I hope it's not like 1 hour early or like different. Just please put it on the Google. Like the events.
oh yeah, I mean, yeah, I'll message the thing with the last time is that Gonzalo also well we kind of are finishing here, so I'll tell Alex to stop the recording because it didn't work for me, so I just told it to tell him to stop the recording. Anyway, so what was I saying? I don't remember what I was saying before that. Yeah, so hopefully next week we just have the author and they can explain their paper and that will be easier. But yeah, I'll try next time. I have to run the reading group myself and read the paper myself. I'll try posting more and asking if people have something to say more often. I feel like what usually happens when I do that is nobody says anything. I just keep reading the paper. But
yeah, maybe like sometimes I just have no opinion to give, and so I'm just a little. I'm just trying my best.
Yeah, I think that also it's probably if I pick some easier paper, it's more likely more people will have.
Yeah, I noticed how
opinions.
the easier to understand papers have more conversation. The harder ones, just nobody can understand it enough to give a question.
Yeah, I guess for the harder ones, it probably would be better if people actually read the paper beforehand. But I mean, we started, people were supposed to do that. We started, but I know in practice nobody does that, so I stopped bothering people to read the paper. And maybe I will have to really try to understand it and like have something prepared for something like that. But yeah, I don't know. For the simpler ones, yeah, it's easier for everyone to just say things. I think I like how much people talk in the. I think it was fun for the anthropic paper. The one with all of the circuits and whatever. I think that was pretty interesting. And yeah, sometimes the authors come and people ask interesting questions. That's cool too. But yeah, we don't always have to get the authors. Also because I don't always I note that I don't always remember to even try. Like I guess I could have asked the authors for this paper. I'm not sure that will help a lot. Also, this kind of I think it's easier to get Mech Interp people than this kind of academic that writes this kind of paper. But yeah. Anyway, let's see anyone else has anything else to say. I think we can just leave it here because it's been like an hour and 30 minutes or something. So yeah. This recording hasn't stopped yet, but I'll try stopping it later. Otherwise, I don't know, we'll just put it later on YouTube or something. But yeah, anyway, goodbye.
Bye, nice to meet
No, I didn't hit you, but no, anyway. Goodbye.